Aneutronic fusion propulsion. Introduction. Space exploration is limited by existing propulsion technology. Up to now, chemical rockets have been used to reach low Earth orbit, the Moon, and the outer regions of the Solar System. Chemical rockets can use either solid or liquid fuel. Regardless of the type of fuel, their design is similar to that shown in Figure 1. Oxygen is combined with hydrogen or a hydrocarbon fuel in a combustion chamber where high temperatures and pressures cause the exhaust to be ejected through a supersonic nozzle to provide thrust to the rocket. The momentum of the fuel ejected through the nozzle provides the force or thrust that accelerates the rocket forward. There are many variations of chemical rockets, but they all suffer from the need to carry copious amounts of fuel. Other methods have been proposed to decrease the need to carry such a significant mass of fuel into space. Ion drives, for example, are used to provide the very low thrust required to maintain satellites in Earth orbit. The fuel that they carry is xenon gas accelerated by electric fields. Nuclear fission propulsion has been proposed for space missions, and thermal nuclear fission reactor rockets were constructed and tested at the Nevada test site through Project Rover between 1956 and 1971. In these rockets, a nuclear reactor provides heat to liquid hydrogen through nuclear fission and ejects the hydrogen gas through a Laval nozzle to generate thrust. While these rockets must still carry hydrogen fuel as a propellant, these rockets can provide more than twice the performance of chemical rockets by using heat through fission rather than reactive chemicals. The results of the 72 reactor tests conducted under Project Rover were very promising and culminated in the successful 12-minute test of the Phoebus-2A Nerva, nuclear engine for rocket vehicle application, reactor that generated over 4 gigawatts of thermal power. One problem associated with nuclear fission rockets is radioactive contaminants. These contaminants in the exhaust make this technology impossible to use in launching payloads from Earth. Additionally, for applications in space, radiation protection must be provided for the crew by adding heavy shielding materials or by locating the crew as far as possible from the reactor propulsion system. Nuclear fusion, as opposed to fission, provides another potential propulsion technology. In a fusion propulsion system, isotopes of light elements are fused together under extreme conditions to form heavier elements, releasing large amounts of thermal energy. This thermal energy can be used to heat liquid hydrogen to high temperatures and expand it through a Laval nozzle to provide thrust in a manner similar to that shown in Figure 1. Typically, isotopes of hydrogen and helium would be used in fusion propulsion systems. Deuterium is an isotope of hydrogen and can be separated from the hydrogen in water. Fusion reactions are difficult to initiate due to the high temperatures and pressures required. Thermonuclear bombs, for example, combine a fusion device with a nuclear fission bomb to provide the high temperatures required to initiate the fusion reaction. Regardless of the conditions required to induce nuclear fusion, the energy release is large. From propulsion standpoint, an advantage of fusion over fission is that for a given amount of thrust, the fusion reaction requires less fuel than either fission or chemical propulsion systems. Fusion reactors using deuterium or tritium fuels are easiest to initiate, however, they generate significant amounts of neutron radiation. This is a hazard for the crew on a spaceship, and there is a high probability that neutrons produced by fusion reactors would escape into space without providing much of their energy to a hydrogen propellant. Other fusion reactions using isotopes of helium and lithium will generate only charged particles, such as protons, that travel very short distances before giving up all of their energy as heat. These aneutronic fusion reactions take place without neutron production and decrease the need to carry large amounts of radiation shielding material for the crew. The energy from charged particles generated by a neutronic fusion can also be captured in conductive coils and converted directly into electricity. Aneutronic fusion promises to be an important mechanism for future space propulsion, although novel accelerator or laser systems must be researched and developed in order to initiate, sustain, and control the fusion reaction. Another futuristic method of spacecraft propulsion involves the use of antimatter. Antimatter includes antiprotons, antineutrons, and positrons, anti-electrons. Although this propulsion process may be the most efficient, antimatter has some drawbacks. For example, antimatter is generated in only minute quantities at accelerator facilities around the world. Although it has been captured and stored, containment remains a problem. When antimatter combines with matter, it completely annihilates and converts to energy, which then can be converted into heat for a propulsion system. Antimatter reactions provide the greatest amount of energy per unit mass of any potential fuel, but the ability to generate significant quantities of antihydrogen or similar antimatter fuels at any accelerator facility is very limited. The focus of this study is on aneutronic fusion propulsion. Integral to this study are the topics of fuel, rocket design, and the organizations that research aneutronic fusion development. Comparison of specific impulse for various rocket designs. Chemical rockets. Chemical rockets burn solid or liquid propellant. The exhaust gas exits the rocket through a Laval nozzle and generates thrust. Figure 1 provided the outline of a liquid-fueled rocket using liquid hydrogen as the fuel and liquid oxygen, LOX, to combust the fuel. Unlike turbofan and ram engines, rockets are not air-breathing and must carry their own oxidizer. The Laval nozzle is a principal component of chemical rockets. Its design is based on compressible fluid flow theory. Degree in general, the nozzle is made up of contoured convergent-divergent cross-sections. Conical cross-sections are also sometimes used. Its purpose is to transform pressure energy into kinetic energy. Nuclear fusion rockets may also make use of Laval nozzles by heating up a liquid propellant and ejecting it as a supersonic gas. In subsonic flow, fluid can only be accelerated by decreasing the cross-sectional area of the duct section that it is traveling through, as in a Venturi tube. Once the velocity in a fluid reaches the speed of sound, Mach 1, the fluid can continue to accelerate only if it is expanded. The Laval nozzle combines a converging section where the flow is subsonic, a throat where the flow is accelerated to sonic speed, Mach 1, and a diverging cone where the flow is accelerated to supersonic speed. The performance of a rocket is based on its thrust, where T equals dm/dt, x exhaust, and by maximizing the exit velocity, the thrust reaches a maximum. The pressure of the combusting gases in the combustion chamber directly affect the amount of thrust that the rocket can achieve. Whether a rocket is propelled by gases from combusting propellant or by gases heated through a nuclear fission or fusion reaction, two equations determine the thrust of the Laval nozzle. The maximum mass flow rate through the nozzle can be computed in terms of the nozzle area, athroot, the combustion or heated gas pressure, pp, and the heated gas temperature, 2. Ion drives. Ion thruster electrical propulsion provides a convenient and efficient method of generating thrust. A gas that is easily ionized, such as xenon, is carried on board as a propellant. The voltage difference between an electrode and a metal screen accelerates xenon ions toward the screen and out the back of the spacecraft, generating thrust. The specific impulse of this kind of drive is about 3,000 seconds. It is relatively common for satellites to use ion drives, generating minute forces measured in millinewtons, to maintain orbit. Solar energy and radioactive decay are possible sources of electric power for satellites in Earth orbit. In deep space, fusion or fission reactors could provide electrical power. However, once the xenon propellant has been expended, the ion drive is no longer useful. Ion drives include the VASIMR, Variable Specific Impulse Magnetoplasma Rocket, designed by the Ad Astra Rocket Company in Webster, Texas. This system uses two RF radio wave antennae to couple energy into an ionized gas that is used for propulsion in space. While ion drives are often used to help maintain orbit for satellites circling the Earth, the VASIMR technology has been proposed for use in moving payloads throughout the solar system. The specific impulse for this technology is cited as 5,000 seconds compared to -3,300 seconds for typical ion drives. Photonic propulsion. Photons of visible light, infrared radiation, or X-rays can produce thrust through momentum transfer, where the momentum of each photon is given by P equals HA, h, Planck's constant, I equals radiation wavelength. Photonic propulsion has been explored by YK Bay Corporation, http://www.ecorp.com, who holds a patent on a photonic laser thruster. These drives generate no contaminants and require a source of electricity to produce photons. Their photonic laser thruster, PLT, uses an active resonant optical cavity formed between two mirrors on a pair of spacecraft to generate thrust. Photonic drives would be viable on fusion or fission-powered spacecraft if their power output were used to generate electrical power that could provide light. Radiation shielding. Radiation shielding will be important for astronauts traveling to the Moon, to the other planets, and to other star systems. Radioactive particles and cosmic rays left over from the Big Bang, radiation from supernovae, X-ray emissions from black holes, and a constant flux of energetic protons from our own Sun all contribute to the radiation dose received by humans in space. Radiation levels are typically measured in sieverts, SV, expressing the amount of energy deposited in human tissue from radiation. 1 sievert is equivalent to 1 joule of energy absorbed for every kilogram of tissue. 5,5 An older unit, the rem, Roentgen equivalent, man, is still in common use. 1 rem equals 0.01 sieverts. Sieverts are now the international standard unit. The energy absorbed is strongly related to the amount of radiation damage done to the tissue. On Earth, the magnetic field of the planet helps to shield people from most of the effects of radiation from the Sun, but cosmic radiation and terrestrial sources of radiation, granite, potassium, radon gas, all contribute to an annual background dose that everyone receives. The average annual dose of radiation in the United States is about 2.5 mSi from background and another 1.0 mSi from other source, such as dental X-rays, commercial jet flights, and radiopharmaceuticals. The total annual dose in the United States is approximately 3.5 mSi, millisieverts, per person. In space, away from the protection of the Earth's magnetic field, the radiation dose increases substantially to about 250 mSi per year. The radiation dose in space is continuous, and the effects of being in space for extended periods of time may be cumulative. As a comparison, 2000 mSi of radiation in an acute dose can cause significant medical problems and 5000 millisieverts is usually fatal. Leukemia and other forms of cancer are possible for people exposed to chronic doses of radiation at the levels encountered in space. The logical conclusion would be to carry radiation shielding into space to protect the astronauts. The problem is that shielding it is typically heavy and expensive. 4 types of radiation must be shielded. 1. Gamma rays, Y. These are energetic forms of electromagnetic radiation, photons, and tend to penetrate most materials. High-density metals, such as iron, lead, and uranium are usually used to shield gamma rays. 2. Beta particles, P+, P, E. These are electrons or positrons, the antimatter counterpart to electrons. They are emitted by the radioactive decay of certain isotopes and through nuclear fission. Because these are charged particles, they are fairly easy to stop with minimal shielding. 3. Neutrons, N. These uncharged particles are generated by nuclear fission and fusion. They may penetrate metals, yet they can be slowed down until they decay in light materials that contain hydrogen or carbon. Typical shielding material includes water, paraffin wax, and polyethylene blocks. 4. Heavy charged particles, P, A. Ions are atoms that have one or more of their electrons stripped from their outer orbital. Due to their positive electric charge, ions are generally easy to stop within any kind of material, unless the ions are very energetic. Typical ions include protons, which are ionized hydrogen atoms, and alpha particles, which are ionized helium nuclei. Cosmic radiation includes heavy ions emitted by exploding supernovae and may include ions as heavy as iron nuclei at extremely high energy. Long-duration spaceflights will require copious amounts of water for the crew, and water can be used to provide some shielding from neutrons for the astronauts. Shielding material for gamma rays presents a weight problem. Lead is one of the best shielding materials for gamma, but at a cost of about $10,000. 16 To launch material into space, lead shielding is expensive to use. The International Space Station and other spacecraft designed for long-term human habitation usually have a small area that is heavily shielded to prevent excessive radiation exposure to the crew during solar events. In addition to the dangers of natural sources of radiation in space that can endanger human health and safety, the propulsion techniques of nuclear fusion and fission generate large fluxes of radiation. Neutron production is of special concern because neutrons can penetrate metals and the structural material of space habitats. The general equations that govern radiation shielding can help develop spacecraft designs that will minimize radiation exposure.